Okay, hello. My name is John Heun. I'm a research specialist here at the University of Arizona, stationed at the Maricopa Ag Center, and I work for Pedro. My background is in electronic systems engineering, and I'm the person who put the electronic components together, as well as some of the mechanical fabrication to get these sensors mounted on the tractor platform. So now that we've gone over tractor platform and sensor considerations, um, now we need to integrate everything. So major considerations for system integration from my perspective is what sensors are we going to use? The sensors that were chosen for this project were the IRT for thermal, sonar for plant height, and spectral sensors, which were the crop circles. So another consideration. So some of the questions: what do we use for measurement and logging? What's a good system? How many channels are we going to need to get all these sensors hooked up? What we used was a Campbell Scientific CR3000. That's where we started, and we used that for our analog sensors, which our sonar was an analog output, current loop, 0 to 20 milliamp current loop, and our IRTs were also analog outputs. So we put those guys on the CR3000, and for the spectral side, we left those on Holland's GeoScout to run those, and I'll get into why we did that later. But these two logging systems were separate, but we were still linking them and synchronized at the same time with GPS position data. Another consideration: how fast do we take measurements? What's going to be the scan rate with this data logger, and what's possible and what is practical and necessary at the same time? Where are our limitations? Data logger, is it the sensor response? Is it perhaps the GPS output frequency? Or is it the speed of the platform in the field? I mean, as far as productivity goes. So there are many possible solutions here, but what we're going to talk about is the one that we custom tailored for what we wanted here with a drought study, and talk about what we had to deal with regarding some of these hardware and software issues. Okay, so here we have a system diagram of our setup. We have our spectral sensors connected to our GeoScout logger. Information was stored onto a 256 megabyte SD card that in that unit. And then on our analog side, we had IRTs and sonar units interfaced originally with our CR3000 because we only had a few sensors and plenty of channels on there. And then as we expanded the system, we ended up adding a CR1000 instead of going with a multiplexer or buying a larger capacity data logger. So to those two loggers, we added CF card modules, and they make storing and downloading data to the office PC very fast, and they're very convenient and well worth, I think, the $100 or so that they cost to add those to those loggers. Very convenient. So although there are some limitations to deal with on our Campbell units, I really love using them. They're probably my favorite piece of equipment out of all the equipment that we have here. They're built very well, very rugged, dependable pieces of equipment. They've been pretty much the backbone of our electronic measurements and all the projects that we've been doing here at the university over the last 6 years. So here we've got all three loggers linked to a single GPS receiver, in which we have used both Trimble, an Ag GPS 332 RTK receiver, and also a Hemisphere Outback A320 in different seasons. And here we're splitting the signals on the cables, creating basically a parallel circuit carrying all the digital data. So let's talk about measurements and communication. Analog measurements can be done extremely fast, much faster than digital. And when I say digital, I'm talking about the serial communications. for higher rate sampling, and that's, relatively speaking, faster than say 2 hertz. It's a good idea to use sensors that have proportional analog output, such as a current loop or a voltage output, than serial sensors. So in our case, what I chose to do is not mix the digital and analog outputs in our application. We kept them separate and on their own loggers, and we paired similar sensors on the same logger. And so we had IRTs all on the CR3000 because it had more channels and we needed all those channels. And so with there not being any room left over, we moved all 4 of our sonar sensors onto the 1000. So for example, I experienced a case where adding a second serial port to the logger. So on the logger, we've got an RS-232 port, and those GPS signals are coming into that port and being read by the logger. And so what I was attempting to do was bring in another stream of serial data onto a separate port on the same data logger, both data incoming at 5 hertz. And what happened was that because of limitations in the data logger, my sampling frequency, which I had programmed for 5 hertz, could not go faster than 2 hertz. So that data logger is needing more time to handle strings coming in on more than one port. So trying to minimize that and just using the serial port for GPS was the best thing to do here. So I'll get into another important aspect of this a little later. Serial sensors will be the limiting factor of the data logger scan rate when trying to achieve higher rates while using analog sensor outputs at the same time. So they're just slower in nature than analog outputs. So the concept I want to highlight in this slide is that we can share one GPS unit with multiple data loggers and synchronize them by geographical position data. So I'm saying synchronize loosely here because depending on exactly when each data logger is in its scan cycle and it's ready and receives a complete GPS string, the GPS receiver may have updated its position, and one of the loggers or 2 of the loggers may grab a slightly different position, but it's a very small difference when we're talking about a speed of 5 hertz. Okay, in this example, we don't have to worry about too much about the specifics here because this was for a different project in which we were using an RS-232 network on a grain combine before we did this phenotyping work. But just to illustrate a point that here again we're splitting up the same GPS string, we're using the same wire, and we're splitting it up to 3 different what I would say a listening device that only needs to record those GPS strings and doesn't need to send any kind of feedback information at all. So we can just share the same lines of communication and not worry about any kind of data interruptions or a loss of information. So the voltages that are on these wires are high enough, and the resistances in the wires are small enough, and the cables are at short enough distances to be able to complete these without any kind of problems here. Okay, so we can easily configure the GPS receiver to output and send multiple strings over our RS-232 network here and choose which one we want to use and ignore the rest. So we typically use the GGA string with the Campbell's, and Holland's GeoScout data logger requires GGA and RMC strings for operation. So as far as programming on the Campbell side, simple is better. There's just less headaches to deal with. So I suggest picking a single string. We use the GGA string again with the best information for your particular purpose, and just go with that one. Now on this slide, we have our RS-232 network synchronizing our loggers and our crop circle sensor network, which operates a little differently. The crop circle spectral sensors communicate with the GeoScout logger over a serial network, which is a RS-485 protocol and similar in nature to a CAN bus. In this case, sensors are pulled for data so that only one can speak at a time, and we don't have any clogging of data on those lines. So information can move, in this case, in both ways on the same set of cables. So these protocols are implemented in order to prevent data loss. So what we chose to do was, instead of trying to integrate those sensors into the Campbells, we chose to just keep it separate on its own data logger so that we could get the system operational and get to the field quicker. It's not impossible to get that done, but much faster, and we already had those components there. The main difference here, the main problem, I would say, with interfacing those sensors to Campbell's is that their baud rates, the speed at which data bits are passed on that network, are incompatible with the standard rate baud rates on the Campbells. So there has to be basically another piece of hardware created to do that kind of an interface. So now let's look at these NMEA strings coming from the GPS and look at a couple common strings here and just see what kind of data are in them for those who aren't familiar with that. The first string we have here is the GGA string. So number one, we've got latitude data, and that's in the first two numbers are degrees, so that would be 33 degrees. And then the next two digits are 04, which are the minutes, the whole number, the integer portion of the minutes. And then we have the decimal point and then 8 digits after that, and that's the fractional portion of the minutes. So actually what the latitude here is 33 degrees, 4.42373 minutes north. And then we've got the same thing. We've got longitude here. And then number 3, we've got quality. So for differential corrections, that would be a number 2. And in this case, we have a number 4. So that's RTK corrections. Position number 4, that's 12. We've got 12 satellites there. Number 5 is an indication of the precision in the horizontal plane. And number 6, another important one, is our elevation above sea level. And then we've got the RMC string below that, some more redundant information here, latitude and longitude again. Number 9, we've actually got a speed in knots, and 10, we've got direction in degrees, and that's in relation to true geographic north. And then we've also got a date stamp there in position 11, which it could be useful, and the Holland system uses that particular one to set files. So, and then we've got the GP VTG string. So again, we've got direction. We've got 2 different speed values there. So let's get a little bit into software. Campbell loggers have an operating system that can compile their CR basic code, and they run measurement and control programs on them. The piece of code that I have here was designed to read in a single GPS string, which is the GGA string, and make sure that logger is accurately capturing that entire string so that we can parse all that data out and get exactly what we want in a reliable way. So another important thing that it's doing here is making sure that all 8 decimal points in the previous slide, the minutes portion of the latitude and longitude data, are going to be preserved. So I have to deal with Campbell's own data types for those of you who are familiar with programming. And in order to overcome that problem with the data types cutting off 2 digits of precision. So instead of, if you try to put that string and save it, parse it out and save it as a decimal point, it ends up cutting off 2 digits there, and those 2 digits are what get us into the centimeter level precision. So that was a pretty important thing to do in order to keep all those 8 digits. So what we did was just ended up breaking it up in a way where we're saving all of those numbers as whole numbers, as integers, so that we can keep all of the digits that are available there, and then we just put them back together in post-processing, which is a really simple procedure. So here's an example of an output file from a CR1000. In the red box, we can see the GPS information split up and all 8 decimal digits are recorded, which you can see looks like an integer. There's not a decimal point there. Also, we have recorded other relevant and important GPS data in the other columns just to the right of that red box. In this example, in this part of the data here, the tractor is actually in motion, and if you look at the elev column, which is elevation, you can see that there's very small changes, at the centimeter level as that tractor's transversing the field. And if it was, this is RTK correction, so and you can see that in the quality column with the number 4 there. There's 4s all the way down, so we know that it's in RTK mode, and the very small differences in the elevation show that. So if it was differential correction, we'd have much bigger swings, up to 1 meter, 2 meters, even larger than that, which in our cases, for trying to calculate plant height, we need that really high level of precision. So also these other types of data, the quality, the satellites, the horizontal dilution of precision, those can help us troubleshoot and even filter out bad data if we had a problem with satellite coverage at a given time. Okay, same table here. We mentioned previously issues with sensor response, update rates, and sampling frequency. So here's an example where we had the data logger scanning the sensors at a rate of 5 Hertz, which you can see in the timestamp column there. So it was recording GPS positions, sonar sensor, and in this case, a laser ranger. So the sonar's update rate was set ASAP in its software, and the laser, which was also configurable, we set that update, I think it was about 100 Hertz. So if you look at that, both sensors are providing a current loop analog output, which is turned into a voltage using a precision 100 ohm resistor at the data logger. But what we're seeing here is the sonar unit's response limitation is about 2 Hertz. So we can see repeating numbers within a 1 second period of time, while we have a new number in the laser column every 200 milliseconds. So this can be undesirable, but also a benefit at the same time. Although we may want to have a 5 Hertz response from that sonar sensor, the important thing here is that we are not limited to sampling both sensors at 2 Hertz. We're not getting hung up by that sonar sensor because it's an analog input or an analog output from it that we're reading. And there's always a signal present in the current loop type analog output. So we've got flexibility here to make measurements at higher speeds to collect what we may deem more important data, like for the laser, for instance. So, but at the same time, it also brings a question that, is 5 Hertz really a reasonable or necessary scan rate when one of our sensors can't provide new data that fast? So some things to think about there. Okay, so considerations. For data loggers, we're looking for something rugged, something field ready, can handle vibrations, has for a computer, is it a solid state hard drive, something that's not going to skip and get hung up. We like saving to memory cards because we can easily move that data from the tractor to the office computer. Data loggers, the number of channels, how many sensors are we going to be using? How many channels are they going to need? Those IRT sensors, they take 3 channels each, and the sonar sensors, they take 2 channels each. So then you're adding a ton of sensors, those channels get used up pretty fast. So there's different options there. You can go with a logger with a bigger capacity, or you can break it up into smaller loggers, and you can use those loggers for different projects down the road instead of just using them for this type of an application. which for a smaller project, that might be, like a CR9000X might be totally overkill for the kind of measurements you need. But we can save money and we can be resourceful, maybe use these loggers from other experiments that we've done, other data collecting events, and just bring them together for this kind of a project. And we can do that, and there's no problem doing that because we're going to synchronize all that data, which is measured independently by those loggers, with the same GPS signals. We should use analog sensors with analog outputs, current loops or voltage. Or current loops, we're just turning them into a voltage because that's what data loggers can measure. And we have that way we have the ability to make really fast measurements. I would suggest, as far as programming goes, keeping calculations to a minimum, save complex analysis for post-processing. Just keep it simple. And then also on the safety side, these systems can get pretty large pretty quickly as far as the electronics go. So having a dedicated driver, may be necessary depending on how you build the system and how much user interface is required during sampling. So there's only so much they can do, and it needs to be a safe operation. Some final remarks. A flexible design. This system has a very flexible design where we can use these loggers and all these pieces for other projects, and then we can reassemble and bring them together in the summertime to do these kinds of projects. And so we're not just limited by one type of hardware that can only do this and it can't do anything else for us. So we can be resourceful in how we put these things together. We're using existing equipment and materials. On the tractor side, we're using, instead of fabricating brackets and mounts from scratch, we're using things that are already available for the agriculture sector. We can just buy them, put them on, get the sensors on there, save a lot of time. They give us a lot of flexibility to be able to get things level or make adjustments and move them into positions where we think we would like to do sampling. On the electronics side, research your sensor specs carefully. Sometimes commercial claims can be a little deceiving. I don't want to point any names out or anything, but like if a sensor is they're saying better than 1 hertz of an update rate, then you shouldn't think that you're going to be able to get 5 hertz of a response out of that thing. So somewhere in the middle there you might be able to get something, but just be careful on that. And then just keep it simple. Just keep it basic and don't go too crazy with trying to see everything you can get, what's possible. Just start simple, and then you can move up from there. So then, as far as some of the work that we still have going on in this, we're working with our collaborators at USDA, ARS. We're exploring low-cost sensors and GPS options with Jeff White there. We're helping with some preliminary testing of a LiDAR system with Andy French and Bob Strand. And finally, we would like to thank Cotton Inc. for their support on this project. Thank you.